Good morning, students. Today, let us discuss the topic on Fermi's Golden Rule. Fermi Golden Rule. It's very important topic as far as quantum mechanics is concerned. So, this is also very important title in time dependent perturbation theory. So, very important equation that we are going to obtain. This equation that connects the experimental side and theoretical side directly. One such equation. So, Fermi's Golden Rule refers the transition probability between two states. Transition probability between two states, in the sense it can be either ground state to excited state, or it can be excited state to ground state. So, actually speaking, it refers the transition probability per unit time. So, which is nothing but a Fermi Golden Rule. So, transition probability per unit time is directly proportional to the square of the perturbing field and the density of states. So, two factors involved in Fermi's Golden Rule. One is the square of the perturbing field. Perturbing field already we know already. When light interacts with the matter and we have a perturbing field. So, because of the perturbation, we have the perturbing field. So, we know about perturbing field very well. So, this is very important factor. The another factor is density of states. Density of states, probably which you have studied in solid state physics, which refers number of states in the final one, in the final state, or number of electrons occupied in the state in the final state, final level. So, this is called the density of states. So, the transition probability per unit time is directly proportional to two factors. One is the density of states, the other one is perturbing field, the square of the perturbing field. Perturbing field mainly refers as the matrix element. So, we know about the perturbing field. It's a matrix element sandwiched between Bra and Ket vectors, initial vector and final vector, normal wave function and the complex wave function. So, generally we will take normal wave function as a ground state, and for the excited state we will go only with the complex wave function. So, this is what we know already. So, one is the matrix element. Of course, as I said earlier, there is a connection between experimental side and theoretical side. When Niels Bohr was working on experimental side, so in the year 1911, he could figure out the structure of the atom, the stationary orbits of the electron in an atom. At the time, he had a lot of data. He had plenty of data in which he could obtain the intensity of spectral lines of a hydrogen atom. He had a lot of data. So, when Werner Heisenberg joined with his team, and he took the data, the experimental data, and he converted into matrix elements. And of course, we know that Werner Heisenberg, he was well versed in mathematics, especially matrices. So, we know that a matrix element, which consists of the low and high, what we call this as initial and final one, row and ket, Bra and ket, rows and column vectors. So, we know about this one, and diagonalize the matrix will give you diagonal values. So, these values are eigenvalues. These values are eigenvalues. So, the values which he obtained, Werner Heisenberg, which are exactly equal to the values which Niels Bohr obtained. So, both the values match with each other. One is experimental side, other one is theoretical side, using matrices. Both the answers match with each other. So, diagonal values of energy eigenvalues or whatever may be, those values exactly the values which were obtained by Niels Bohr. So, that's why I said this Fermi's Golden Rule exactly resembles with that invention, that is the experimental side, which is exactly equivalent to the theoretical side. Okay. So, Fermi's Golden Rule. So, it was proposed by Paul Dirac in the year 1927, Paul Dirac, and he kept the name Fermi Golden Rule. Golden Rule, he has kept as Golden Rule. He could have kept as Fermi rule. So Fermi Golden rule. Golden rule, as I said, the very important one is, the first one is, this is one such equation that connects experimental side and theoretical side. That's the first one. And this is not only applicable for quantum mechanics. The same rule can be applied for material science, chemistry, solid state physics, biology, including life. My God, Fermi's golden rule can be applied for life too. How it is possible? Because we said transition between two states. Fermi's golden rule refers the transition between two states, that is ground state and excited state. We have also same thing. We have the transition between two stages, positive and negative. So everyone will have negative, everyone will have positive qualities, ups and downs, plus and minus, low and up, okay, cause and effect. So all those things refer only golden rules. So that's why I said that Fermi's golden rule can be applied for life too. So that's why it's termed as Fermi golden rule. So today we are going to discuss the Fermi golden rule, which is very, very important as far as this unit time dependent perturbation theory is concerned. So it refers the transition probability per unit time, which is directly proportional to two factors. One is density of state, another one is the square of the perturbing field. The square of the perturbing field is nothing but square of the matrix elements. Okay, so that's all. So an explicit expression for the transition probability per unit time is calculated below. So we are going to have the transition probability per unit time, which refers the transition to a continuum value. We know that all stationary states in an atom will have discrete in nature. So all stationary states, when it is perturbed with some external perturbation like electromagnetic waves or magnetic field or electric field, then the electrons will gain the energy from the external perturbation. It will go to the excited states. We know already this. So this is one such transition from ground state to excited state. So in a ground state, as I said, this is discrete in nature, stationary states. And in the excited state, there will be lot of levels which are merged to each other. They will be very close to each other. What we call this as continuous energy levels, continuum. So all the levels, they will merge together in the excited states. Okay, so one is discrete in nature, another one is continuous. One is summation, the another one is integration. Is it clear? So summation means discrete. So we have stationary states in an atom. So they are all discrete in nature. We are going to sum all the probabilities of the electrons in the stationary states. Whereas when you go to the higher state, excited state, these levels, they will merge together. We are going to integrate. So summation will be replaced with integration. So very important concept. Okay. So continuous means it goes to the upper level. Okay, excited state. Of course, from excited state it will transfer into ground state. That also we have two levels, two level systems. Okay. So transition between two levels means from ground state to excited state, as well from excited state to ground state. So here we are going to assume that the system is enclosed in a cubical box of side L. So cubical box we are going to take, which has boundary condition at its walls. The stationary states of the system are discrete. We know just now we discussed. So but separated in energy by an interval which is inversely proportional to the volume of the box. And we are going to assume that, we are going to consider that the box is infinite. Okay, the energy interval increases and merges into a continuum system. As I said, when the atom in the system is perturbed, the electrons will gain the energy and it will go to the excited state, and these excited state and they will merge to a continuum states. Okay, if it is infinite, very large. This result can be used to calculate the probability for transition that involve states in a continuum. Okay, the probability of transitions involve between two states. The probability of transition of mth level, this is a final state, is given by this equation. So we know already this equation. The probability between two states, transition probability between two states is given by square of the amplitude square. So we know already square of the amplitude. So which is equal to a square of the perturbing field multiplied by the phase factor. So we know already this, and we have already discussed the graph earlier in detail. So graph mainly refers that it has a more contribution, the more effect only at the central peak of probability distribution of electrons. So this has more effect only at the center. Okay, because the highest amplitude occurs only at the center. When omega becomes omega ml, when omega ml is very close to 0. Okay, so omega ml, we know that omega ml equals Em minus El divided by h bar, we know it, because E equal to h bar omega, we know already this eigenvalue equation of energy. So omega ml, m stands for final, L stands for initial state. So omega ml equals Em minus El divided by h bar. So as I said just now, the central peak will have more contribution. Just now I said. So it means that Em minus El, which is almost equal to 0, that means Em equals El. So when Em equals El, this has a more contribution. When Em minus El is very large, this will have less probability, less contribution. I repeat. So here at this region, we have Em is almost equal to El. At both the regions, Em minus El will have less contribution. That means Em minus El is very large value. Okay, so this is what it is given in the paragraph. The probability is the largest for those states in which the unperturbed energy Em0 are close to El0. They are very close because of the factor 1 by omega ml square. Since the levels are very close to one another, they form a cluster. So here we have a cluster around Em is equal to El. When Em equals El means omega ml approaches 0. Okay, and the probability is very small on either side. So probability is very less. Less contribution will be there, less effect will be there on either sides. So when Em is far away from El, so Em minus El is greater value, we will have only less effect. Okay, since all other levels represent nearly the same physical properties, we may add the probability. So we are going to add the probabilities. Okay, so we are going to add the probability amplitude. So if we start in the state L, then the total probability of transition is equal to summation over Am of t, which depends on time. So this is probability amplitude. We have studied already in first order correction in time dependent perturbation theory. So which is nothing but your sum of probabilities. So now we are going to get the Fermi Golden rules equation in two ways, two methods. One method is without dealing delta function. Another one is with dealing delta function. So two methods we are going to discuss. The first method goes with the lines. We are not going to use delta function. Okay, without delta function. So we are just interested in the rate of leaving L and occupying any state K or for a continuous distribution. That is, we are going to have the system. We are going to have the system in which the perturbation will occur. So this will go from L state to the higher state. This will go from ground state to the higher state. So that's why I said, see, these levels are very close, and this will have continuum and this will have discrete. Okay, so this is excited state and this will be your ground state. So this is initial state psi L. This will be your excited state M. Okay, so for a continuous distribution, now we consider the density of final states. We are going to consider the density of final states. Density of final states, as I said, probably you would have studied in solid state physics, which is nothing but number of states between the energy E and E plus dE. Number of electrons occupied in a state is nothing but density of states. You just remember, this is your ground state. Due to the external perturbation, it goes to the excited state. So population will be more in the excited state. Correct? In the final state. That's why this is a final state. So density of state mainly refers the number of levels or number of electrons in a state in the final, at the final state. So rho of Em dE refers the final state where the population is more. Okay, so now we are going to consider the density of final states is given by this. So Nm is the number of final states lying between the energy ranges Em plus dE, which is given by this expression. So Nm equals rho Em dE. That's why I said number of states in the final states. Okay, number of electrons occupied in a state in the final states. So this is nothing but given. The total probability from transition in each state is obtained by multiplying this amplitude square by this. So your total probability is nothing but product of this and this. You have density of states multiplied by the square of the amplitude. So that will give you your total probability. Okay, this is nothing but total probability. Transition from between two states. Now we are going to substitute equation 7.69. So 7.69 is given by this. Okay, 7.69. So I have written here 69 in 7.70. So 7.70 is here. Okay, so t is given by this. We have the expression already, this expression. So you just substitute here. Now look at the limit. Limit goes from minus infinity to plus infinity. Okay, it refers at t tends to infinity. T tends to infinity means omega tends to 0, omega equal to 2 pi by t. It refers only at the central peak around. Okay, t tends to infinity, it refers omega tends to 0. It refers only central peak. Central peak only will have the maximum contribution. So this refers only the central peak. Okay, so the limit goes from minus infinity refers only t. Okay, time. So it refers that omega equal to 2 pi by t. It's inversely proportional. So you have t equals 4 pi by h bar squared. You have mod squared, perturbing field squared, density of state multiplied by the phase factor. Okay, here there is a continuum of final states and we have chosen the limits minus infinity to plus infinity. Since EM is broad relative to transition probability t, that is observation point is t is relatively very long. Now we know already E equal to h bar omega, we know already. So here it is E equals h bar omega because the system is not compatible. So you remember that E equal to h bar omega. So remember, okay, it is not h omega because system is not compatible with h bar. Okay, don't forget this is h bar omega. Okay, is it okay? Clear? So wherever h is there, you just think it of this is h bar. System is not compatible with. Okay, with the presentation. So E equal to h bar omega. So differentiating this will give you dE equal to h bar d omega. Okay, so we know that EM minus EL equal to h bar omega ml. We know already this. Correct? EM minus EL equal to h bar omega ml. You substitute here. So we have T 4 by h bar square h1 ml. 1 stands for first order perturbation. M stands for final state. L stands for initial state. And we can pull rho EM out. Okay, we have dE equals h bar d omega. Okay, h bar d omega. And we can write instead of dE, you can write h bar d omega. So h bar d omega. So I have written as. Okay, this h bar and this bar will get cancelled. You have 4 divided by h bar h1 ml square rho e of m and this phase factor. Is it okay? So this is your phase factor. We are going to solve this phase factor and multiply, we will get the transition probability. So this, as I said, this is a central peak. 4 sine squared omega ml t by 2 divided by omega squared ml is a central peak, which is the domain of integration, energy conserving transition. The main contribution comes from only from this peak. So central around. Now just take this factor as f of omega ml. So f of omega ml equals 4 sine squared omega ml t by 2 divided by omega squared ml t omega. Now I can substitute this factor as x. Omega ml t by 2 is nothing but your x. So omega ml equals cross multiply will give you 2x by t. Differentiating will give you dx with respect to x. So 2 by t dx, this will become dx. Substitute here. Okay, substitute d for d omega, you can substitute here, and this factor can be replaced with x. And omega squared ml can be replaced with 4x squared by t squared. Is it okay? Omega ml squared equals 4x squared by t squared. See, 4x squared by t squared, where 4 is here. Sine squared, instead of this term you will have x. D omega can be replaced with 2 by t dx. Okay, and these 4 and 4 will get cancelled, and t and t squared, 1t will get cancelled. So you will have 2t sine squared x divided by x squared dx, and of course this is standard integral, the value of standard is given by pi. So 2 pi t. So we have obtained the central peak as 2 pi t. Is it okay? This slide. Okay. Now the equation 7.73. So we have obtained that this value is given by 2 pi t. So t equals 1 by h bar. Don't forget this is h bar. 1 divided by h bar square of the perturbing field multiplied by density of states, and we have obtained the value of the central peak is nothing but 2 pi t. Okay, I can bring this t to this side, okay, left hand side. So transition probability per time, which is nothing but this factor W. So WML refers transition probability per unit time, which is nothing but Fermi Golden rule. So we have remaining term 2 pi by h bar modulus square and density of field. So as I said, the transition probability is equivalent to 2 by h bar, the square of the perturbing field multiplied by density of states, which is nothing but Fermi's Golden. Is it okay? And this factor, the perturbing field, is nothing but is given as matrix elements. So matrix elements, which is nothing but sandwiched between Bra and Ket vectors. So Bra and Ket vector, initial and final one. So initial wave vector usually will take as a normal wave vector, normal wave function, and for the final one in the excited state we will go only with the complex wave function, complex vector. Okay, rows and columns. So this was the contribution given by Werner Heisenberg to Niels Bohr. So he has taken the exact values from the data of Niels Bohr, and he could obtain exactly the same result of Niels Bohr's data. So that's why I said this is the equation which exactly resembles with the experimental equation. So this is contribution given by Werner Heisenberg. Okay, the experimental data are given by Niels Bohr. So this is the diagonal value. We will have to get the diagonal value. These diagonal values only are eigenvalues. These eigenvalues are the results which Niels Bohr had obtained. Okay, intensity of spectral lines for a hydrogen atom. Okay, so this is first method. So first method is very simple method and also elegant method, and the second method in terms of delta function. So we are going to deal the same result in terms of delta function. Of course, delta function is very, very important concept. So whenever you find EM is very close to EL, we will have delta function, which will have an answer. So that's why we are going to discuss in terms of delta function. So